We're looking at problem number 1 on the test. I think the hard part for most people on this was the idea that it was occurring at an angle. So if we look at this, our triangle here is a similar triangle to here, here. And our normal force is perpendicular to the surface. It's always perpendicular to the surface. But in this case, it's perpendicular to the surface and not the entire weight component, because weight always acts toward the center of the Earth. So our weight component is acting toward the center of the Earth. So our similar triangle here puts weight as the hypotenuse of this triangle. Our leg, then, of this triangle is equal to our normal force. That makes our normal force equal to mass times gravity times the cosine of theta, this being theta. Our weight is mass times gravity, so the weight of the victim is 882.9 newtons. But the normal force is some component of that. So we've got to find that component. So the normal force is going to equal the 882.9 newtons times the cosine of 60 degrees. So our norm is equal to 441 newtons. Now, similarly, our weight acts centered down toward the center of the Earth, so there is some gravitational component here for our victim. There is a force of gravity in this direction. So my force of gravity is going to be parallel to the surface, or this way. And if we use this triangle, this force of gravity is equal to this leg of the triangle, or force parallel. So our force parallel, then, is equal to mass times gravity times the sine of theta. So our force parallel equals 882.9 newtons times the sine of 60 degrees. And our parallel force, then, is 765 newtons. Now this force parallel is going to also be our force due to gravity. That's going to be the weight, because part of the hill is supporting the weight component. Not all of it, but part of it. So this leg, or this piece, is going to be our force due to gravity. Now that we have those broken down, let's tackle the problems. So A says, how much work is done by friction as the sled moves 30 meters along the hill? So A says friction equals, no. A says, what is the work done by friction? Well, we know work is force times distance, so the work done by friction will be the frictional force times the distance. And then remember, we need to look at that cosine of the work in relation to the distance that it's moving. So we have the cosine here. No, we don't. We can figure this out though. We have the distance of 30 meters right there, but we don't have the force of friction. But we do know the force of friction equals mu times the normal force. When we know our normal force is 441 newtons, so our force of friction equals mu, which was 0.100 given to us in the problem, multiplied by 441 newtons. So our force of friction is 44.1 newtons. So then that comes back up here. So our work done by friction equals 44.1 newtons multiplied by 30 meters, because it's going 30 meters down the hill. Now, to take this component into account, this piece into account, this direction, our victim is being lowered down the hill. So the direction of motion is down, but our friction force is acting up or against the direction of motion. So our friction force has to be at a cosine of 180 degrees. So the work done by friction then is the multiplication of those numbers, and that turns out to be a negative 1,323 joules. B asks us how much work is done by the rope on the sled. So B is saying, what is the work done by the rope? Okay, well, the work done by the rope is equal to this tension force here. Now, here's the thing. The work done by the tension force should be equal and opposite to the work done by the weight component because it's traveling at a constant speed. Except we have this frictional force in here, right? So this frictional force is helping to keep the work done by the rope to be a little less. So these two added together equal our weight component. Well, we already know what our weight component force is. We don't know the work done by that, but we know what the force is. So the tension in this rope is going to be 765 newtons minus our 44.1 newtons. So we have the work done by the rope equals the 765 newtons minus the 44.1 newtons times the distance, 30 meters, times the cosine of 180 degrees. Because again, this is acting in the opposite direction to the direction of motion. So the work done by the rope equals 627 joules when we do that calculation. C then says, oh, sorry, this should be a negative, my bad, because we have the cosine of 180 there. C says, what is the work done by the gravitational force? Well, we already know the gravitational force is 765 newtons, so simply the work done by gravity is the force of gravity times the displacement times the cosine of 180 degrees. But gravity is this force right here, acting in the downward direction, the component of the weight. So it's acting in the same distance, in the same direction as the displacement. So the work done by gravity is 765 newtons multiplied by 30 meters multiplied by not the cosine of 180, but the cosine of 0. So that's just 1. So that goes away. So the work done by gravity equals 22,950 joules. D then says, what is the total work done? So work total equals all of these pieces of work added together. So we get a negative 1323 joules plus a negative 21627 joules plus a 22,950 joules. So the total work done equals 0 joules. Now, if you think about that, the total work done equaling 0 joules, because we're traveling at a constant speed, because we have no net force acting on this individual, all said and done. So our total work should equal 0 joules.